Okay, now we are going to start seeing the MMF distribution when we have a sinusoidal distributed coil. So here is the formula for the number of turns in a sinusoidal distributed coil. So we have that we are going to have the peak MP times the sine of the angle. So if we want the number of coils in this angle E epsilon x, we just need to apply this formula. But how about if we want to find the distribution in the whole coil? So we can look at just one little angle, the epsilon x, and we are gonna have that our small coil, or not small piece of the coil, is gonna be equals to MP. The magnitude, just gonna write the magnitude of MP sine. We still have the epsilon x times, we are looking for this area, DES, and we care about the magnitude of this. So if we want the number of turns total, is gonna be equals to, we have to integrate both sides, so we are gonna have, and we are gonna integrate from 0 to pi, so from 0 to pi, we're gonna have MPS sine epsilon x ds dx the epsilon. Okay, so this is just gonna give us NHT NS equals to MP S MP this S doesn't go here, I just wrote it because we have sine there. Okay, MP, the integral of sine is minus cosine, so we are gonna have minus cos pi plus cos of 0, and this is just gonna give us that the total number of turns is gonna be 2 MP. Okay, so this is for our phase A. If so, MP sine ES. For our phase B, it's just gonna be 120 degrees shifted, so we're gonna have ES minus 2 pi over 3, and NCS is gonna be equals to MP sine ES epsilon x 2 pi over 3 plus 2 pi over 3, and this is our shift of 240 degrees. Okay, so this is the basics. Let's start looking at how we can get the distribution. So let's imagine that we are only care about these points. We don't care about the whole distribution, we only care about the distribution in these points. So we are gonna have that for this one, we are gonna have here that, remember, we said that if we go from cross to dot, we said that is positive. So up to here, we are gonna have positive. And then we're gonna have positive for both. So we're gonna have positive for this one and for this one. So this is gonna be, we know that our MMF in the gap is equals to Ni over 2, and so Ni over 2 plus Ni over 2, we are gonna have here the whole, we just get rid of the 2, so we are just gonna have here MP sine epsilon DES. Okay, and for the bottom part, it's gonna be the same but negative. So negative MP sine epsilon des, epsilon x des. Okay. So now from this point to this point, we know that one of them is going to be positive because it's still going from cross over here to dot, but the other is going to be negative because it's going to dot to cross. So it's going to be 0 from here to here because one is positive, one is negative. Now from here to here, they are both negative, so we're going to have both negative. And from here to here, we know that one is going to be positive and the other going to be negative, so we are going to have 0. And from here to 2 pi, we are going to have both positive. So this is how the MMF is going to look if we just consider those 2 points. Okay, but now how about if we add another one right here? If we add another dot here, and we add another dot here, and we add another cross here, and another cross here. Okay, so we know that these are the dots and the crosses for the red one. So if we do the same for the green one, we know that it's going to be slightly bigger. So we are going to have here the dot for the green one, another dot for the green one, cross and cross. We're going to know it's a slightly bigger because the angle is going to be bigger here. So we know that this is a little bit bigger than the red one, but it's going to follow the same way. Yeah, the same geometry. So we know that it's 0 from here. We know that it's a little bit bigger here. And if we add another one, let's make a blue one. Here, another dot. And here, another dot. Here, another cross. And here, another cross. Now we know that here is pi, and here we are going to have 2 pi. So we know that they are going to keep growing until 2 pi, and then they start decreasing. Okay. So now we know that here we're going to have a dot of blue, and here another dot of blue. We're going to have our cross and our cross here. And it's still slightly bigger because it's below 2 pi, so it is still increasing. 0 in this part again, but then again negative here. And it goes back to 0 here, and again positive here. Okay. So what if we wanted to get the MMF in the green point here? What if we wanted to get the MMF here in this angle, let's call it alpha? If we wanted to get the MMF here, we know that the one that is adding to this point is the blue one, because the green one in this point is 0. So only the ones from alpha to 2 pi, all the other that we add here up to 2 pi because they keep increasing are gonna be the ones that add to this MMF. So if we want the MMF at that point alpha, we are gonna have the integral from 2 pi to alpha, so this part, sine epsilon x. Oh well, we're gonna have first our MP sine epsilon ds times I. So this is our distribution. Oh well, this is what we have here. Our MMF times our current is what give us our MMF. Our number of turns as our current give us our MMF. Okay, so this is just equals to, we take out the constants, and we're gonna have here 2 pi epsilon. Here we're gonna have sine epsilon x. This is epsilon x. Well, they're all epsilon x. And the integral of sine is minus cosine. So we're gonna have here MPIA minus cos of pi over 2 plus cos of of alpha. So we know that our MMF in our angle alpha is just going to be MPI cos of alpha. Okay. So now let's try to apply this into an example to find the inductance. So we want to get the self-inductance of this coil. So the first thing that we have to do is find the flux linking the coil. Going from cross to dot. Second, we need to find the flux linkage. And with the flux linkage, when we divide the flux linkage by the current, we find the L, that is flux linkage over current. Okay, so let's start doing this. We know that flux is equals to MMF over reluctance. So our reluctance now that we have a small angle the epsilon is going to be G, or air gap, mu naught RL, length of the conductor, times the 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 epsilon x. Okay, so our flux is gonna be an integral from our angle ES to ES minus pi. Yes, ES to ES minus pi. Multiply, and the integral is gonna be m pi a cos alpha. This is our MMF, what we just found out before. And we divide by our reluctance, so we're gonna get mu naught LG d alpha. Okay. Oh well, here let me change this ds for alpha, so everything is in the same terms. Okay. So we have that our flux is equals to MPI mu naught RL over G multiplying the integral of cosine, so sine ES minus sine ES minus pi. Okay, and if we follow the trig identity that sine ES minus pi is equals to minus sine ES. Okay, I keep writing yes when we're talking. Oh yeah, ES because we are integrating from ES to pi minus ES. Okay. Okay. So if we do this trig identity here, we are gonna have 2 m pi I multiplying our mu naught RL over G sine ES. Okay, so this right here is really important, and this is our self-inductance. Remember, this L is the length of the conductor. Okay, so we have flux linkage now. That is multiply our number of turns by our flux. And we know that our number of turns is going to be MP, number of turns N. It's going to be MP, the peak, sine epsilon S T E. That is what we just find out. So this is going to be equals this times what we just found out here. Okay, now we are doing all of this with respect to the phase A, right? So that's why this angle is just yes. So if we do it with respect to the phase A, and we know that our number of turns is just this, just to make it clear. And here we're gonna have dE. So we need to integrate this. And we're gonna have MP squared, yes, IA mu naught RL over G integral now, since we are doing first phase A, we are going from pi to 0 to pi. So we have here 2 sine square, because we have sine here, 2 sine square, ES dE. Okay, so this is equals to m pi squared IA mu naught R over G. And when we do this integral, well, to be honest, I just plug it in MATLAB. So to do it an integral in MATLAB, you just call your function, you just call your variable, you define it using this expression, sims. Then you declare your expression, in this case is 2 times sine x squared. Our solution will be the integral of the expression from, and you define from where, from 0 to pi. And this gives me the result. Oh well, I need to take out this, so it shows this pi. So all of this is going to be times pi. And now to find our inductance, we know that we just divide this by our current. And now we are going to have that our self-inductance in A is going to be, in A dash is going to be this. Okay. So let's look at another example. Now, instead of one pole, we have 2 poles. And we want to find the sinusoidal distribution in the winding, and in the windings, and we want, we have sinusoidal distribution in the winding, a smooth air gap, and a space between the phase of 120 degrees. Okay, so let's draw it first, so we have a little bit clear what is going on. So here in 0 degrees, I'm gonna have my phase A. Now, notice that I'm writing capital A. This means that here is where the peak of the distribution is, of the turns is going. But we know that this is a sinusoidal distributed, so we are gonna have a smaller like here. So it's just like the example we did here. right here. So we know that it is distributed, but so I don't have to draw all of this. I just draw capital A and capital A dash where our crosses is. And we know that 120 degrees we're gonna have our B. So this is 0, this is pi, this is gonna be 2 pi over 3, and this is gonna be, this is a cross, and this is gonna be B dash, and it's gonna be a 5 pi over 3. Okay, so this is how our coils are distributed. Okay, so they are asking us to find the inductance of A based on B, of the current B. Okay, so we know that we already figured out that the flux due to a current is equals to 2mp. So we have here the current B that is producing it, mu naught RL over G sine epsilon x. So this is what we figured out here. Here, the self-inductance of a coil. So this is the self-inductance produced by B. Okay, so now we have to find the flux linkage. So the flux linkage will be the number of turns in B times this current produced by B. The current in A produced by B. So we are gonna have that this is equals to, well, we need the number of turns in B, and we already figured out that the number of turns is this. So we have the number of turns in B times the self-inductance of the inductance produced by of the flux produced by the current in A in B. And now we need to integrate this. Now, where do we integrate this? We are gonna do it with respect to A, because remember that we need we are looking for the flux in A with respect of the current in B. So this is integrated through A. It's very similar to the other examples that we have done. Just went out. We're going to integrate from pi to 0 because we want the flux we want the flux linkage with respect to A. Okay, so here we're going to have MP flux AB equals to MP squared IB mu naught RL over G 0 to pi 2 sine yes minus 2 pi over 3 times psi yes. Okay, so now this is gonna be equals to MP squared IB mu naught RL over G, and again I just plug this into MATLAB. So I'm gonna comment this part. And so here we have 2 sine yes. So the solution is pi over 2. Okay, so this is the other way around. We're going from 0 to pi. So this is minus pi over 2. Minus pi over 2. And when we calculate our inductance, E to B, so we divide by B, and we're gonna have that, we're gonna have minus mp squared mu naught R over G times pi over 2. And this is how we find the solving the mutual inductance of these two coils. Okay, now we have this exercise. It's asking us to draw for a phase A of 4 poles. We want a MMS distribution in space that is a square rectangular wave, and we want an MMF distribution in space that is sinusoidal. Okay, so let's start with the square wave. Here we are gonna have, we know that it's a 4 pole, so they are gonna be distributed in 90 degrees. So we are gonna have something at 0, we are gonna have something a pi over 2, we're gonna have something at pi, we're gonna have something at 3 pi over 2, and we're gonna have something at 2 pi. Okay, so we are gonna follow the convention that when we go from cross to dot is positive. Okay, let me draw here circle so we can think about where we're gonna have. Okay, so let's say that we have one in the maximum distribution. Oh well, right now is just a square, so one of the coils here, so we know that we're gonna one of the coils here. So, yes, so if we want from 0 to pi over 2 to be positive, okay, we are gonna need something at here. If we have a cross in 0 and a dot in pi over 2, we are gonna have, let me see, if I have here a cross, so from cross to dot is gonna be positive, so from 0 to pi over 2, we are gonna have positive MMF right here. Okay, now from dot to cross, so for pi over 2 to cross, that is gonna be 2 pi, the MMF is gonna be negative. Okay, now we're talking. Okay, now we know they're separating by 90 degrees, so we know that we are gonna have something here and something here. So let's say that we have another cross here at pi, and we have another dot here at 3 pi over 2. So we follow the same convention. We say that from cross to dot is gonna be positive. From the rest, we are gonna say that is negative. Okay. So now we can see that from 0 to 2 pi, one of them is negative and the other is positive, so they are gonna be 0. From 2 pi over 2 to pi, we are gonna have that they are both negative, so they're gonna add up. From pi to 3 pi over 2, we have that they are both one positive, one negative, so they are gonna be 0. 3 pi over 2. From 3 pi over 2 to 2 pi, they are both positive, they were both negative, so we are gonna have the distribution. And in terms of the magnitude, this is going to be minus ni because we are adding 2 ni's over 2. Okay, so this is how we can get the square wave. And we know that to turn this into a sinusoidal, we need to distribute this right here and distribute this. So we have a capital A and capital 2A. So this will be just the same example that we already have done here, where we found the equation for MMF when we have distributed sinusoidal. So we just need to distribute this to coil sinusoidally, and we will get the sinusoidal distribution of the MMF. That is it. I hope this helps.